All right, welcome to From Program to Process. What happens after the compiler? Everything all right? Good. Okay. My name is Anders. I work in Norway in Civid, where we make these cool robot eyes, and I mostly do C++ there these days. And I also run this website called cppquiz.org, which is a C++ quiz site. And if you're into C++ quizzes, there will be a C++ quiz during the party this evening. And I also hang out on Twitter quite a bit with these various accounts, so you might find me there later if you want. But we're not here to talk about that. We're here to talk about what happens after the compiler. And to figure out what happens after the compiler, let's start with a simple function. And the simplest function I could think of was just this one, int main return 1. And before we start looking at it, I have to say this talk is specifically about Linux. So I'm running these slides on a Mac. It's probably quite similar. And I'm sure there's something of the kind on Windows as well, but I don't really know. But this is specifically about Linux and specifically about x86-64. If anything is unclear on the slides, please ask during the talk while the slides are still up there. But if you have any questions of the kind more, I would like to know some more about this, and I'm also interested in them. Please hold those to the end, because chances are that we will get to them during the talk. Who has used Compiler Explorer? Yeah, quite a lot of people have used it, and we use it quite a lot. So to figure out what goes on with our code. So I took my function here, I pasted it on Compiler Explorer, and it gave me this. So there's going to be a bunch of assembly in this talk, but it's only 2 or 3 instructions that we're actually interested in. And we're going to skip the rest, and I'm going to explain the things we need. So if you don't have any assembly background, you don't need it, so don't worry. This function, there's just some stack bookkeeping stuff at the beginning and at the end. And the only interesting thing in this function is this single instruction. This is the entire body of this function. It says move EAX1. And this means to put 1 into the register called EAX. And EAX is where you're supposed to put your return value. So this is very simple stuff. If you compile this, you link it, and you assume that works, and it gets loaded somehow, and the process starts up, and it shuts down and everything. There's nothing surprising here. This is going to exit with 1, and there's really nothing interesting in the function itself. But I think the function is getting a bit complicated, so I figured I'd refactor it a bit and extract this compute function to compute the return value. So now we have the main function, which calls compute, and then we have the compute function, which computes this value 1. And then I just pasted this on Compiler Explorer again to see what's going on behind the scenes. Well, it gave me this. It gave me the assembly for the compute and for the main function. The compute function is exactly identical to the main function we saw on the previous slide. It has the same declaration, the same body, so it gets just the same assembly code as well. The interesting part of it is where it puts 1 in the return register. The main function, again, has all this stack stuff that we don't care about right now, and then a call to compute. So it's quite simple. But how do you call compute? Right? You're a CPU. You don't know anything about names or functions or labels or anything like that. Call compute, that doesn't mean anything to a CPU. So how does the CPU actually execute your stuff? So here's a very simplified illustration, but I just put 7 dummy instructions in memory here. Instruction 1, instruction 2, etc. And then there's 1 actual instruction in here, or kind of actual. And then here's the memory address. So at memory address 0, we have instruction 1. At address 4, we have instruction 2, etc., etc. And then over here is a register in the CPU, which is called the instruction pointer, RIP, also commonly referred to as the program counter. And that is just a 64-bit value which just says, well, this is the next instruction I'm going to execute. So it's just pointing at the next instruction. And when I'm going to execute instruction 1, I first just bump the instruction pointer to be ready for the next one, and then I go do whatever instruction 1 is. So that might be move or add or something, whatever, right? Then we bump the instruction pointer, we execute instruction 2, we bump the instruction pointer, and then we do the instruction 3, which is a jump. So it says jump to 20. And that just updates the instruction pointer to, okay, I'm going to point over here instead. And then we bump the instruction pointer and execute instruction 6, and so on. So it's very, very simple stuff that the CPU can do. It knows about registers and memory addresses. And you can tell it to point to some other place in memory. But the CPU has no concept of function names, right? So what is it Compiler Explorer does not want us to know? That's what we're going to find out in this talk. So let's compile this program ourselves and not link it, just compile the object file. So compile the object file like this, and then I have a main.o. So let's just have a look at main.o. Let's just hex dump main.o. And these are the bytes. It's just an object file, just a bunch of bytes. And if anyone can read this stuff, then you don't need to be in this room, right? But there is some stuff we can read out here. There's this 7F, but then we have the ASCII values for E, L, and F. 4.5, 4C, 4.6. That's ELF in ASCII. And those ELF, that stands for the executable and linkable format. And that's the binary format you have on Linux for object files, binaries, libraries, stuff like that. And other Unixes as well. It comes from, I think it's from Solaris in the 80s or something. It's been here for a long time. But hex dumping is not the way to look at an object file. There's a much better tool called objdump. I gave it the options W for wide output, capital D for disassemble everything, and R for show relocations, which is something we'll get back to. And then I said, please use Intel assembly syntax because I like it better, and most people seem to prefer that syntax these days. So let's objump this file. And then it goes disassembly of section text. That's the first thing it says. And the text section is where the code is. So all the machine code gets dumped into the text section. Then you have other sections like data sections, you have some headers, you have your debug symbols, your symbol table, lots of sections. But now we're going to look at the machine code, and all the machine code lives in this .text section. So here again we see the compute function. And now we can actually see these are the bytes of the compute function. So everything is just bytes, right? So here we have these bytes here, and if we look down at the hex dump, we can see, well, F30, F1E. So here is our compute function in the actual file. And objump is just grouping these bytes by instruction. So we get one instruction on one line, and the assembly equivalent to the right. So F30, F1E, FA is the NBR64 instruction, and so on. And then it puts down the memory address here. So at address 0, we have this instruction. At address 4, we have this one. At address 5, we have this, and so on. So that's how to see, to look at the output from objdump. So here is our move EAX1 again, the thing that puts 1 into the return register. And the instruction, the opcode here is B8. So that's the instruction that says, put an immediate value into this register. Take out like a normal number and put it into EAX. And the number we're going to put is this here. So why isn't the 1 over at this end, right? It's just a 1. It's not like a huge number. And that's because x86, which I'm on here, is a little endian architecture. So we take the least significant byte and put it at the lowest memory address. So this is address 9, A, B, and C. So we put the smallest byte here at address A. So that's how you put. That's how you look at the machine code for putting 1 into EAX. Then we have the main function. And as we've seen before, there's a bunch of stack bookkeeping stuff, which we're not interested in. And there's a little curiosity here. It's putting 0 into EAX. And that's because in C and C++, if you don't return from main, you forget to write return, it's supposed to return 0 for you automatically. So that's how you get that done. It just puts move EAX 0 at the beginning. So then if you forget to actually call something or return something, it will already be 0. And that, of course, gets optimized away. Everything I'm doing here is on O0. And now, finally, we get to this call thing that we were wondering, like, how can you call compute? And E8 here, the opcode, is the call instruction. And then we're going to call whatever operand you give it, which is 0. And that's the address of compute. But that's just a coincidence. This doesn't actually work. It's just a coincidence that we have these zeros here because the compiler can't actually know what value to put here. The compiler doesn't know where compute lives. It can't answer this question. And the reason is, in this diagram, I'm going to show this many times during the talk, it illustrates that you have one object file over here with a header, a text section, a data section, and a bunch of other sections, and another object file down here, file 2.o, which probably then came from file 2.c, with some text and data and some various sections. And then the linker is going to combine these object files into one executable. So it's going to take all the text sections and stick them together here, and all the data sections and stick them together in the data section. So any addresses that you have in the object file, they will be different in the executable. And then finally, this executable gets loaded in memory somewhere. So you have some memory down here, and oops, here's our executable, and some more memory. And it's impossible for the compiler to know where things end up in the end. So the compiler has just gone, well, I'm going to put E8 for the call instruction, but then I'll just put zeros because I don't know, and I'll just put down a note. So someone coming after me, can you please fill in the actual address here? So it's put down this little note which says something about compute, and that's called a relocation. And relocations are the notes that the compiler puts down for someone else to fix up the actual addresses. And relocations is one of the main topics of this talk. So this is exactly the same as from the previous slide, just copied it over here. So we can see, again, the object output for main.o. Still not an executable, just the object file. And the trick is then that we don't know where stuff is going to get loaded in memory. But the linker knows where in the executable everything will be relative to each other. So the trick we can do is to use a relative call. So the E8 here, the call instructions, instead of saying jump here, it's going to say jump this amount of bytes this way or that way in memory from where we are right now. So that's how we kind of survive loading. But then we have to see here in the executable if we can figure out the correct offset to have from the executable here. So these are just the bytes in the text section. So there's no room for this note. This note isn't actually in here. This note is just objump showing it to us. So in here, in the actual code, we only have room for the call instruction and the operand. That's all we have room for in here. And the note is off in a different section. And readelf is a nice way to look at that. So if you say readelf -r to show the relocations in an object file, and then W for write output, we get a list of all the relocations. All the things that the compiler didn't figure out has an entry in this table. And we only have one, so there's only one entry in my table here. But it says here, relocation offset 1D. So that means at 1D, so here 1C, so that means here, 1D, there's a relocation to be done. And then it has some information about what kind of relocation it is. And the linker doesn't have to understand assembly or machine code or anything. The linker just knows at 1D, I have to fix these 4 bytes to point to the right place. That's all it has to know. And then what value, or what's the name we're going to resolve here? And that's compute -4 for some reason. And then you can see up here, objump has just taken this information from the relocation section and just inlined it here in its output just to help us to see that there's a relocation here. But there is no relocation inside the actual text section. So what's going on with this -4? Well, let's try to do this relocation manually. Just by looking at the object file, let's see if we can do the relocation ourselves. So we're about to execute this call instruction. So if you remember what happens first? Well, we bump the instruction pointer down here, and then we execute it. So let's resolve the relocation. So the relocation is at 1D, compute is at 0. So we have to jump from 1D to 0, so that's -1D to compute, but the instruction pointer is already going to be down here. So we have to compensate for these 4 bytes that, since the instruction pointer is already in the future, right? So we have to go -4 and then -1D to get to where compute is. So -1D, -4, that's -21. That's how to do a relocation manually. Let's see what the linker does with this. Now let's link this. Now we take the object file and we link it into an executable called main, and then we just object jump main with the same options that we had before. And we see basically the similar thing we've seen before, but the addresses have shifted a bit here. It doesn't start on 0 anymore. It starts at 1129, because when you make an executable, there's more stuff going into it, like some startup routines and stuff. So it has shifted a bit, and I've just omitted a bunch of stuff here, so we can just look at our two functions again. And here's our call instructions. Again, our E8, the relative call, and you can see the relocation is now gone. And object jump is being a bit helpful here, and it's saying call 1129. So that's where compute lives. But if you remember, E8 is a relative call. So this is not 1129. This is object jump is just showing us what it will be when you compute the actual address. So this is still a relative address. This is just object jump being helpful and showing what it will be when you turn it into an absolute address. So we got -21, and the linker got dffffffff. And what does that mean? Well, we are in a little endian architecture. So if we just swap the bytes around, so we get big endian notation, which we're more used to, then it's a bit easier because this is a signed integer. And the way you represent a signed integer is to use 2's complement. So if you take this number and run it through 2's complement, there's our -21 that we saw earlier. So the instruction pointer is going to be at 11.4a, and then we're going to jump -21 up to 11.29. And indeed, if now we have compiled and we have linked everything, let's try to run our program finally, and it exits with 1, which is what we expected it to do. But when we were looking at just the object file, we figured out it was 21. -21. We didn't know what the linker knows. We just knew this just by looking at the object file, which the compiler knows everything about. And in fact, I said the linker is going to reorder these sections. So it's going to like squash all the text sections in one place, all the data sections in one place, but the linker is not going to mess around with each section. So every section stays intact internally. Any relative addresses inside of a section are still the same in the executable. It's just between the sections that is not true. So the compiler actually knew all along that it would be -21 to get to compute, to this compute function. But by the time we get through the linker and to dynamic linking, in the general case, we can no longer be so sure that this is the compute function that we're going to call. There might be some other compute function that we actually want to call in the end. So in the general case, the compiler just has to leave a relocation here just to be sure in case it's not actually this compute function that we want in the end. So what we can do then, let's try to make it static. Let's give it internal linkage. So this function is no longer visible outside of this compilation unit. We don't get any symbols for it that the linker can mess around with. So now static int compute, internal linkage, and main is going to call it. We compile and overjump this. And then we can see the relocation is gone. So just in the object file, now the compiler went, okay, this is safe. I know this, it's -21. It's not going to change. It's always going to be this compute function, not some other one. So I can put -21 here. All right, so then we know enough about relocations to do them manually, and we can go take a job as a linker somewhere. But what if there are more files? Okay, if it's that hard to call a function in the same C file, in the same compilation unit, how hard is it if you bring more files into this picture? So here's the same program again. We have main here in main.c like before. Then I extracted this compute function into a new file called library.c. And this will get compiled separately. And then I just have a header file to forward declare it. So if you compile the library first, that's the least interesting part because that's just this function which moves one into EAX. So it's the same as before. What about main? So the main is the one that calls the other function. How do things change when we use separate files? So here's main. Looks very familiar. Here's the call thing with the relocation. It looks very familiar. And in fact, it is identical. So if you have one, if you have many object files, it doesn't change. It's the same thing. So we don't have to learn anything new. That's wonderful. And why is that? Well, in either of these cases, one or more source files, The compiler always knows internal distances here, but it doesn't know between the sections. And if you have two object files, well, it's the same. It doesn't know where things are going to end up relative to each other. So the compiler doesn't know in either case. And in either case, the linker knows, because the linker is the one linking everything together, making one executable. So the linker is the one who decides where everything gets laid out, and the linker, being the one that writes this file, is also able to change stuff while it's writing it. So the linker has the power to fix up these relocations, and it has the knowledge to do so as well. So let's try to link our two object files. The library.c and main.c were compiled into these object files. We link them and object dump them. And here we have our functions again. They're just in the other order than they were before, and just happen to be so. And we can see that compute is the same. And we can see that the relocation in main, again, has been resolved by the linker. And this time, well, when we're going to call 2. So insertion pointer is going to be down here at 11.3b. Then we add 2, and we get up to 11.3d, which is the address of compute. So when you're jumping forwards in your virtual address space, it's a lot easier to read these relocations, because you don't have to do the 2's complement thing to understand the number. So it's because these happen to end up in this order. And in fact, if I switch around the order of these object files here as arguments to the linker, they will actually also end up in a different order, at least on my Linux system. So that's functions. That's how you can jump to functions or call functions. What about data? Okay, we have seen for functions how the CPU just goes one instruction at a time, and then jump over here, change instruction pointer to point over here, and just keep going like this. And then we use relocations to figure out where stuff actually ends up in the end. But what do we do for data? How can it find data? So there are many types of data. The first type of data I'm going to talk about is function parameters. So I have this function here called arguments, because you have to give it some arguments. You give it a and b, and it returns a plus b. And how do I get those variables into that function? Well, on any system, there's a calling convention that specifies how to get stuff in and out of functions. And on my Linux, and I think also on my Mac, and most Unixes use the system v AMD64 ABI, which specifies how to do this. And Windows has one which is very similar. And they both say, if you're going to pass a couple of ints, just put them in these very specific registers. And that's really cool, because if I'm going to call this function, I'm already using some data. I'm computing some stuff on the CPU in some registers. And I can just make sure that my two arguments are now in these two specific registers. And then I just jump over to this function, and it just keeps computing on those registers. I don't have to put my arguments in memory, and then arguments have to read them out again and all of that. So we can just stick stuff in registers, and specifically, I'm going to take the first two ints and put them in RDI and RSI, because that's what the calling convention says. So let's compile and dump this. And I'm not going to explain all of this, just going to say here, it is picking those values out from EDI and ESI, which is what the calling convention told me to do. And when I'm going to return, I'll just add these two numbers together, and add will leave the result in the first operand. So add will take EAX plus EDX, store it in EAX. And EAX, as we mentioned also before, is the return register. So how do you get stuff out of functions? You just leave them in EAX, and then the caller can just pick up from there and start, keep computing on that value, which is now in that register. So for stuff like this, there is no relocations needed, nothing complicated, no addresses and anything. But that, of course, only works for small things like ints, right? We only have this many registers, and we only have this big register. So if you have more than 6 ints or something big, that, of course, doesn't work. So what if we make this other function? It still takes an int as the first one, but then we take a big thing. So here's just some struct, which is too big to fit in the registers. Don't care about what it's like. It's just some struct. And it has a member I, so I'm going to return a plus b.I. So this I member of this big thing struct. And then I compile and object dump this. And we can see that the parameter a is still in EDI, just like before. Just use a register to get the int in there. But getting to this b.I, that's a bit more complicated. So on x86, the stack is growing downwards. So if you have like big addresses up here, small addresses down here, the stack is growing down like this. And by the time we get to this line, then RBP, that's the base pointer or frame pointer, is going to point to, here's my part of the stack. So the stack has been growing down like this, and now it's our turn. Here is our start of the stack. This is our part, RBP. And then I'm going to add 30. But since the stack is growing downwards, right, then when you add 30, you're going to go back into the caller's stack frame. And that's because when you want to pass something into a function which doesn't fit in a register, you just push it on the stack before calling the function. So then the compiler knows, due to the calling convention, where the big thing is going to be on the stack. And it also knows the layout of big thing, because it will have had to see the definition of big thing in order to take it by value. So it knows where in big thing does .I actually live. So then it can figure out, well, our stack starts here, our part of the stack starts here. So big thing is going to be there, and then I is here. So plus 30 to get up to that. And the same is for return values. If it's too big, you put it on the stack. So again, all addresses are relative to the stack, which just grows dynamically. You don't have to think about addresses or relocations or where are stuff in memory or anything like that. It's just very simple, no relocations, no linker involved in this. So that's arguments and return values. What about local variables? So here we have local variable result, which we set to 1 and then return it. And we compile and dump it, as we've done many times now. And here's the assembly. And again, we're going to move, you've seen this before, move 1 into something. So now we're going to move it into a local variable. And this local variable lives at RBP, the beginning of our stack frame, -4. So now, again, we have RBP here. This is our part of the stack, RBP pointing here. And then it's just, the compiler just decided we'll put this local variable in here in our stack frame. So local variables, again, they just go in your stack frame, and everything is relative, again, to the top of the stack. So local variables are also simple. No relocations, nothing complicated with addresses or the linker or anything. So it's all data simple. There's a hint on this slide. Is there any type of data that we haven't talked about? I think I heard someone say globals. And that's correct. Globals, they are not so easy. But we shouldn't use globals, right? But we have some globals. We have our logger, maybe, or some singletony stuff, or some maybe less noble reasons lying around. And what's your favorite global? Yes, that's what I was going to say as well. Std cout, that's my favorite global as well. So yeah, globals, they happen all the time. They're interesting, and we have to talk about globals. And the correct term for a global is that it's an object with a static storage duration. So it means the storage duration that it lives on for, well, almost all of the execution of the program is the lifetime of that one. But yeah, I'm not going to say that every time. I'll just say globals because everyone refers to them as globals, and I'm going to try to finish on time, so I won't say that all the time. So yeah, here we have this function with a global that we're going to return. And then we compile and link this. Now compile and not link it, just compile and dump it, as we've done before. And now we have two sections. We have the text section that we saw before, where all the machine code lives, and then we have the data section where the data lives. And here is our value 2. Okay, so our global lives in the data section here. The first byte in the data section, that's where global lives. And then objump is trying to be helpful. And it goes, oh, bytes, I know bytes, I can translate it into assembly. So this, your 2 here, it looks very much like an add AL byte putter RAX to me. And well, it's just data. But objump is trying to disassemble everything. So that's why it's putting this here. So don't get confused by this, but like everything is just bytes, right? So that's why it does that. So here is our code to return that value. And the opcode here is 8B05, which means take something that lives somewhere relative to the instruction pointer plus some offset and move it into EAX. And something that lives somewhere from the instruction pointer plus some offset, that sounds very similar, right? And that's because it is, again, relocations, they work the same way as for functions. And we can even see here we have the relocation. The symbol to resolve is global and -4 again, because the instruction pointer is going to be down here. So this is exactly like functions. So finding globals is exactly like finding functions in that way, that you use relocations and then the linker is going to resolve it. So let's do that. Let's link this to an executable called main and objump it. And again, we see similar things as before. We have the text section and the data section. Addresses have shifted a bit again because it's an executable with some more stuff in it. And we can see our value 2 down here in the data section, now living at address 4010. And then here is the move instruction, 8B05, move relative to the instruction pointer. And you can see the relocation has been resolved. The linker put in here, well, 2ED9. So we're going to be at 1137 by the time we execute that move. We add 2ED9, which is 4010. So that's how you get at global data. And the question then is, can you, when you have the compute function, we made it static so that the compiler would know to just skip the relocation. Can we do that for data? Okay, I have this diagram again. So the compiler always knows the relative distances inside of a section, but it doesn't know the relative distance between the sections after they have been reordered over here in the executable. So even if the compiler knows this is the global data, it's not going to be overridden by some linker somewhere. Even then, the compiler can't know, because these sections are going to move about when you make the executable. So there's no way to avoid that relocation for the global. Okay, lots of code. I'm going to highlight it a bit at a time, so don't worry. This is kind of for completeness, but also to introduce a bunch of other section types than the .data we've seen so far. I have just a bunch of different types of global data. So first, I have some regular global data, like the one we just saw before, just normal read, write, non-const global data, whatever. One with internal and one with external linkage. And then I have an initialized variable and one which is initialized to 0. And why did I put those two together? We'll get back to that shortly. Then we have another type, which is const. So I have two const globals, one which has been initialized and one which hasn't. And then finally two extern variables. So these are not defined here. It's just a promise to the compiler that, okay, you can compile this. It's going to come from somewhere else sometime later. And then I just have the main function, which just sums them, just to like get some code that tries to access these globals. And I compiled and objumped it, and I cut out a lot of stuff to fit it on the slide. But this is the important part of it. And you can see we have all of these RIP plus 0, RIP plus 0. So all of these are the relocations we've seen. The only two that didn't get a relocation are the two const ones. And that's just because even on 0, GCC decided to do const propagation and just optimize it away, just put the value straight in the assembly, instead of actually going out and fetching those from the global memory. But if it didn't inline them, then it would use the same mechanism. So no matter what kind of global data you have, you get the same type of relocation. Yeah, these two. And then let's look at the data section, where the data is actually defined. So global and internal, the two at the top there, they ended up in the data section, like we've seen before. Normal globals that you can read and write to go in the data section. So you can see here, we have this 1 from global, and this 2 from internal ended up here at address 4. And it shows the names here as well, just to be nice. Then we have the BSS section. And the BSS section is a bit strange. It's for everything that is supposed to be initialized to 0. And it doesn't actually live anywhere in the object file or in the library or in the executable. If I have an array of 2,000 zeros, then I don't put 2,000 zeros in my object file. I just put a note to the loader saying, I'm going to need 2,000 zeros. So when the program starts, can you please make sure I have 2,000 zeros available? I'm not going to put it in my object file or in my executable. And then we have our 0 initialized variable here. But we also have the uninitialized variable here. And why is that? Why did we put that in BSS, which gets zeros? And that's because in C and C++, global variables will be initialized to 0. So normally, like if you should always initialize a variable because otherwise it's going to have an indeterminate value. But for globals, they will actually be initialized to 0. And that's a bit strange because we always talk about don't pay for what you don't use. So you don't want when the program starts someone to go and set like this needs a 0, this needs a 0, right? So the reason we can do this is because when you load the BSS section into memory, you just want a bunch of zeros. So you just request a page of memory from the operating system, and you just map that in as BSS. And when you get a page of memory from the operating system, some other process was using that before you. And you don't want to have processes able to look at the memory of the previous process. That could be like something with a password or some sensitive data. So the operating system is just going to zero out this page before it gives it to you. And that means when you get this, it's already full of zeros. So you just map that page into memory, and all your BSS variables are automatically 0, even though you don't have to actually go and set them to 0 anywhere. So that's cheap and nice. And finally, final section today is RO data, which means read-only data. So we can see our two consts here, the const and const uninitialized. They go down here. So the 3 for that one and the 0 for that one. So couldn't we just have put this 3 over here and this 0 into BSS? Like there are consts, so we can't modify them anyway. Well, like why put them in a different section? And there are several reasons for this. The one really nice thing is if you put it into a separate section, and when you load that section, you put it in a segment which is marked as read-only. If I cast away const from any of these and I write to them, I'm going to get a seg fault. If these were living in the normal global data, and I try cast away const, I write to them, it's just fine. Nothing happens. I just corrupt my data. And crashing my program is just so much better than corrupting my data. So that's one nice thing about RO data. There. Yes. For if you use dynamic linking, that's the other good thing about RO data, and we'll actually look at that in 10 minutes or so. So that's a bunch of global data. Is there any type of global data that I didn't talk about so far? Is there any global data that looks like it's local? We have local, yeah, so they also live in the global data, string literals, but also static locals in a function. So you have a function, you have like static int counter equals 0. That's not going on the stack, because you're not going to get one of these each time the stack grows. It's the same counter all the time. So it has static storage duration. It has to go in some global memory, so you can use the same one every time. And you can also have static class members, right? So you can have a static class member which also goes in any of these. And just to save time, I don't have any examples of local statics and class static members, but they work exactly the same way as this. So all globals work in this way. So here's the diagram again with the object files. I'm going to hide that before I confuse it too much, and I'll get to it. So here's our main.o, the object file. You can see our sections here that we've seen before: text, data, BSS, and RO data. And here you can see it took this 1 and the 2 and put them in the data section. And it took these zeros and like conceptually put them in the BSS, but remember, BSS doesn't really exist. It's just a note that we're going to need them at some point. I took these 3 and this 0, put those in RO data. And these external ones, they're not even defined in this object file because they're going to be defined somewhere else. And then hopefully someone else has some other .c somewhere which actually defines these two variables, right? And so they're going to get in this other object file in the data and RO data section for these two variables here. And then we link all of this. So we can see here in the main executable, we got the 1 and the 2 from this data section in here, and we get the 4 from this data section in here, and so on. And the BSS still doesn't exist. And then finally, we load all of this in memory. So somewhere in memory, all of this stuff gets loaded. And in this illustration, everything is loaded together in one place, in the same order as in the executable, but that's not necessarily so. You don't always get the sections in your executable in the same order in memory. But the really important thing is that it is the linker who decides this order. It's not the loader. So the linker says which order this is going to get loaded in, and the linker doesn't know where, but it knows the relative order between and the distances between these sections, so that it can resolve relocations, and it can know the distance from somewhere in the text down to somewhere in the arrow data here, even though they might be in a different order here, but the linker decided that order. And I also put some permissions here, so that your text section is going to be put in a segment which is read and execute, but not writable, so no one can overwrite your code. And this data and BSS is going to get mapped to read-write, so you can read and write to those, and arrow data is read-only, so we get a seg fault if you try to write to that. And none of our data is executable. So you don't want someone to be able to write some code into your variables and try to jump to it and execute it. And so if you ever wondered, when are my globals initialized? Well, they kind of aren't, right? There's no code that's actually going to initialize your globals, because everything that happens here is just, we're going to take these bytes and just map them into memory. Just load the page into memory with these bytes before even the program starts. So there's nothing in the startup that's going to set your globals. You just start up and you have the loader has just mapped in these bytes. And for anyone doing C++, there's a corner case here. If you have a constructor on a global object, then you generally can't do this. So then there are some functions that get called during startup, which will call constructors for global objects. But for sort of simple fundamental types like this, no initialization is actually going on. It's just load the bytes into memory. And then finally, we get to dynamic linking, which maybe is the most interesting part of the talk. And the difference between dynamic linking and static linking is what is known when. So we have this stage of the compiler, the linker, and the loader. And what can you know about things at these three stages? And an interesting question then is, what can you do at these stages? When can you resolve an address and stuff like that? So yeah, we'll look at that next. So if you remember this one, right? The CPU, it needs addresses of functions, and it needs addresses of data. So it doesn't know about labels and names and stuff. It needs addresses. And if you remember this one, the compiler often doesn't know the addresses, because stuff gets messed up when the sections move around, when it gets linked to the executable. But we also remember that the linker decides this layout. So the linker is going to write this. The linker knows where everything ends up. The linker is the one writing it, so the linker can change these addresses, change the relocations to point to the correct place. But what if we're doing dynamic linking? Okay, so we have this executable, but we also have this shared object somewhere. So I just have this SO1, just shared object number 1. This one also has a header and some text and some data, and this has come from some object files over here, and it gets loaded somewhere in memory. And I have another shared object as well, a shared object number 2, another one down here, and then this one depends on this one, and they both depend on this one. And the linker can't know where the other ones end up in memory. So the loader is the only one who knows where these end up. And the linker is writing the linker could resolve the relocations, because it's the one writing the executable, and it knows where everything is going to end up. But if it doesn't know, what do we do then? Can we then just, let's just leave the relocation for the loader? Okay, let's just not resolve it, and just the loader will have to do this, because the loader knows where stuff ends up. And every time I say, can we just do this then? The answer is always no. Because shared objects really are very shared. It's not just like you get this shared library on the disk, so that these 100 other programs don't have to link all of that code into themselves. They can just load this one, and you save disk space. You can actually also share that in memory at runtime. So when you load a shared object or an executable for that matter, you just memory map the text section right into memory. And if you have many processes that memory map the text section from the same SO, well, they can just memory map that same thing. They just memory map this part of the file, all of them the same thing. So if you have 20 processes running, and they all use this 2 megabyte text section, you have 20 times 2 equals 2, which is nice for memory use, right? So they can all share this one, because it's read-only. So you can't really destroy anything. And the same goes for RO data. You can also share that between processes. So you can't change this, because if the loader was then to, like, I'm going to fix the relocations for this process here. I'm just going to make it writable for a moment, and I'm going to just fix the relocations. And I will. Then you destroyed the relocations for all the other 19 processes, which was using the same code. So you can't go and change that code at runtime or at load time. What can we do? Well, if you remember, we have all these sections with different permissions. So we have the read and execute text, and we have the read RO data, which you can't write to. So these are shared. But every process needs their separate copy of data and BSS, because they have to be able to write to this data without then destroying the data for other processes, so they don't step on each other's toes. So how do we solve this thing with global data? What we do is we use the global offset table. So you might have seen the GOT mentioned somewhere. That's the global offset table. So it's a really, really simple concept. We just put in another section, which is called global offset table. We make it read-write, and we give every process their own copy of it. And in here, we just have one entry for each global variable saying where in memory it lives. So if I have 3 globals, I'm going to have 3 entries here. And then the loader can fill this up when it loads the program. Okay, so the loader is going to load this program. This program has 3 globals. Then the loader puts stuff into memory, and it figures out, well, this global ended up here, this global ended up here, and this ended up here. And I'll put the addresses of these 3 globals in here, so that when the program starts to look for these, it can just look up in the global offset table and find where they actually ended up living. So if I have this simple function called using data, it just uses this data, returns it. This is a global. And then we just compile it like normal, like we did before. And we object dump it, and we see just a relocation here. So it's going to use a relocation for the linker to figure out where data is, but like, where's the GOT? So normally, there is no GOT in here. So what did I forget when I compiled this one? And I want to use it in the shared library. Yeah, I have to say -fpic. That means, that stands for position independent code. So I'm going to say, I'm going to use this in a shared library. I have to make position independent code. So position independent code is going to go look in the global offset table. So that is going to be an indirection, right? Previously, we only got this relocation which the linker resolved. But if I'm going to put this in an SO, I'm going to need to use position independent code and go first look in the global offset table. So now we see we get 2 moves. So first we have one move which looks for the address of data and put that into RAX. And then we have another move which then takes, okay, now RAX is pointing to the right data. So now we can take the value and put it into AX. So we have this one indirection. And then there's one more thing, because like, remember, the compiler doesn't know the distance from the text section to the GOT. So the compiler has to leave a relocation for the linker to even find the GOT. And then it can get the actual value. So it's a bit simpler if we just link this into a shared object and dump it again, so the relocation is gone. Then you can see a bit more clearly what happens at runtime. So what happens at runtime, first, I'm going to look up in RIP plus 2EE8. That's where I'm going to find the data object. So that means I'm up here in the text section, and then I add, what was it, whatever, somewhere in the GOT. There's where I find the address of data. I move that into RAX. And then I can actually go and fetch whatever RAX is now pointing to, which will be the actual address of data. And as I said before, this GOT gets filled by the loader when the program starts. And that's, of course, some tiny cost at startup, right, to fill out the GOT. But normally you don't have a lot of globals. Maybe you have like 4 or 5 if you've been bad. But it doesn't take that much time to fill in this. If you have functions, however, maybe you have an SO file with like 5 globals and 1,000 functions. And you probably aren't going to call all of those 1,000 functions. Maybe you call like 8 of these functions. So then you don't want to do the same thing with functions. You don't want to resolve all of those functions which you aren't going to use. And maybe that SO file, well, that depends on these other 3 SO files. And then these have 1,000 functions. And then suddenly you have actually a startup cost. And it's really important to get your programs, like if you're using C and C++, you're doing systems programming and you want your program to start really quickly. And you don't want to pay this overhead. But also, I don't want every time. So here I have this function which is calling another function 2 times. I don't want every time I call this other function. I don't want to go ask the loader, hey, I'm going to call this function. Where is it? And then the loader has got to go like, oh, yeah, that one. I think I put it over here. And then, OK, that's the address. OK, then now I can. And you don't want to have that happening every time you call the function. So what you want to do is you want to do this lazily. So the first time you actually call a function, you want to do this. I'll go ask the loader. And then the next time, you don't want to do that. But your text section is write only, right? So you can't like fix up your text section the first time you call the function because you're not allowed to write to this text section because you're sharing it with other processes. So what do you do? So you solve it using the PLT, the procedure linkage table, which we'll get to shortly. And here I've just drawn up the sections of our code here. So these are the sections from this SO file. So here's the text section. Here's all the instructions in using function. There's some like stack bookkeeping stuff and stuff. Then I'm going to call function, and I'm going to do that 2 times. Then over here is the text section from some other SO file which actually defines this function. So here's where I want to jump to eventually. And then I'm going to use the GOT again, the global offset table, where I have 1 entry for each global data. So whenever I need a global data, I'll look up in the GOT, where is it, and then I use it. I'll put 1 entry here for each of my functions. So in the GOT, I put the address of function. So eventually, this address of function is going to point over here. So I can just look up in the GOT. Where is my function? Well, it's over here. But, and then we have something called the PLT, the procedure linkage table here. And yeah, so in the beginning, like this address function, it's pointing into our own procedure linkage table. It's just pointing. The calls are going to inside of the house. There's something creepy going on. What's happening here? So let's step through this and see. So I put this little red dot over here. That's the like our step debugger indicator kind of thing. And instead of calling function, I call the function at PLT. So that's just a name. That's just a name that's in here in the PLT. And the linker knows the distance from text to PLT and from text to GOT. So this will all have been resolved by the time we get to runtime. So we just call this function. And then this goes, well, I'm going to jump to whatever address the function is pointing to, which will eventually be here. But now I will jump into myself, which is a bit strange. And the code here in the beginning of the PLT, I'm not showing all the code, just to keep it simple. But what this code does is jump all the way out into the loader. So I'm going to jump out of all of this stuff, and actually I'm going to jump into ld.so, and I'm going to get this function resolved. And what happens in the loader then, or the dynamic linker? The loader and the dynamic linker is the same thing when you talk about dynamic linking. Then the loader goes and does this, oh, where did I put it thing? And then it puts the right address here in the GOT and points it down here to this function. Okay, so we were here in the PLT, jump to the loader, which fixes the address. And then the loader is going to jump to the address it just fixed up. So I don't have to jump back and then do it again, kind of. So then we jump into the actual function that we wanted to do. So we went from our text section into the PLT, look it up here, back in the PLT, into the loader somewhere, and then down here. And these were all jumps. So when I return from this function, I just return to the last call. So I get back here to the next instruction in using function. And then I call the function again. So I call over here to the PLT. The PLT looks up add row function, which is now pointing to the right place. And then we jump over here. So you still have to jump through the PLT and check that value, but it's a lot faster than going through all this loader stuff. So with dynamic linking like this, there's always this tiny overhead, but it's really quite fast compared to the alternative. And then it's time for the summary. So if you have local data, if you have function parameters, you have return values, stuff like that, it's super simple. It just registers and the stack. For static linking, it's also quite simple. It's a bit more complicated. You have to do the relocations. So if you have global data, you have to put a relocation, and then the linker is going to know where it ends up. So statically, the linker fixes this before even the program starts. And for functions, it's exactly the same. Put a relocation, the linker resolves it, and by the time the program runs, there is no sign of relocation. It's just as if you knew all the time. For dynamic linking, if we have global data, we just use the global offset table. So instead of saying, I want this in one move instruction, you say, I want to get the address of this from GOT, and then you go look at that address, and then you get the actual value in a second move instruction. And for functions, we also use the GOT to have the address of the function. It is not resolved at the runtime. It's done lazily by this jump to the PLT. So when the first time you call a function, you have to call out via the loader to get the right address, and the next time you just get the PLT in direction. And that's it. I think we have 2 minutes for questions. Thank you.
So we all share, or with shared objects, you can share the text section, right?
Yeah.
We use ASLR now.
Yeah.
Where does that fit in?
Yeah, so for shared objects, that doesn't matter because they already use position in the question, sorry. The question was, what if you use ASLR? So that's address space layout randomization. So it's a technique which the OS uses to, every time you load a program, you just put it at a random address. So unless you use Frida, I guess it's supposed to make it harder to reverse it, but I'm sure it's easy even then. But yeah, you already have the loader then doing the ASLR thing, so the loader will just fix up the GOT and the PLT. But for your executable, I think you have to compile it with PIE, position independent executable, for it to work with ASLR. I think so, because then you get the position independent tricks also in the executable. I would assume. I'm not 100% sure. I think so. Yeah.
Certain systems allow you to not include the BSS section in an executable in order to save some space.
Yeah.
In that case, I guess it's expanded by the loader approach.
Yeah. So the question is, if you don't have the BSS section in the executable, then the loader will do it, and that's right. If you statically link the BSS, right? How do you do that if you don't? Well, you have the addresses, you have the symbol table. So the text section or the compiler and the linker is going to know the layout of the executable in memory. So even though the BSS section doesn't actually live in there, it is going to know where it will eventually end up being. Yes, it's going to know the size of it and the layout. So if you look at readelf, it will show you all the sections, and then it has a table of which sections are going to get squashed into one segment. And then it has addresses for where these segments are going to go. So one of these sections will then be the BSS. It goes into a read-write segment somewhere, and you just need to know the size. And then the symbol table will know where in this BSS, which doesn't really exist yet, we just know how big it will be, where does this thing live that you're looking for. Yeah, any more questions? Or I think we're out of time. Okay, thanks for coming.